In my front pocket, I usually carry my headphones, my keys, and my knife. But not today because I'm in school. But everywhere I can go that I can legally carry a knife around, I carry my knife.
I don't know if you have to be that prepared, but.
You'd be surprised how it's not like trying to sound practical to use. It's just like it'd be more convenient to put this box with a knife and just take out the keys and try to do it. So you don't need it a lot, but it's usually a better substitute than keys or trying to buy it. You never know. That's not a spread in mine.
To dress up. I like that. He always beat when he's in the corner. So I
Well, I look sexy, okay?
Wow.
I got really quiet.
Alright. Everyone was in silent agreement.
Pretty sure silence in this situation does not.
Emphasizing the silent part of the agreement, but.
Alright.
How you feeling fighting? Fighting is good.
Of course.
Yeah. We're below the store. No, it's not fun. This area, no, it's not fun. Weightlifting.
Yeah, that's good.
Foot's right there.
You can get away with it.
You can bite your way out of the guillotine.
It's a guillotine first off.
Shut up.
Second off, I don't know
Shut
what
the
you're talking about.
grammar nerd.
I mean, yeah, you can.
That's not grammar.
Pronunciation, syntax nerd.
That's not grammar there. It's just called proper beats.
No, he's right. Somebody should know about guillotine.
Yeah, guillotine.
Alright, let's
Just
begin.
corrected his.
I know. I'm hypocritical. 6.
We are going to do example 5.
Yeah, that's a guillotine.
Alright. Yesterday we were talking about improper integrals. We said there are 2 ways that integrals can be improper. The first way is if one of the limits of integration is infinity. And then it's easier to tell it's improper because we can see the infinity right there. The other type of improper integral is when we have an asymptote or an infinite discontinuity within where we're integrating. And we ended with an example of that, and we're going to start with another example of that. So we're going to go integral from 1 to 4 of dx over x minus 2. So this is where we need to be careful from now on. Every time you see a question that says evaluate an integral, you have to think about, is there going to be a problem with this? Okay? It's not going to just tell you in the directions, this is going to be improper. So you have to think about it every time now. Often, if you look at your multiple choice answer options, they'll give you a hint because one of them will probably say divergent. So that would maybe remind you, hey, that's something I need to check for, is that there might actually be a problem with this. But we want to get in the habit of checking every integral that we see now and asking, is there going to be a problem with this? And does that problem happen within our limits? So where does this one have a problem? At 2. And that is within our limits, so that's something we need to be concerned about. If we were integrating this from 3 to 5, then we don't need to be concerned about it. But if that happens within our limits of integration, we need to be concerned, and we need to split it up there. So we are going to take the limit as c goes to 2 from the left, 1 to c. And we are going to add that to the limit as c goes to 2 from the right, c to 4.
Yes.
Then we need to integrate these. What is the integral of 1 over x minus 2?
ln of x minus 2.
The ln of the absolute value of x minus 2?
We don't need
We do need that.
What if it's 1? 2. Can't take the element of a negative number. What if x was 1?
It actually is 1.
That's
true.
What about when x is 1? Yeah, not if, it will be 1. So,
Right there.
yeah, we do need those absolute values here, they are
For
important.
once they're important.
Then we plug in our limits. Upper limit minus lower limit. And this is where, if this was a multiple choice question, please don't write all this out unless you need to. If you need to see this, then you need to do what you need to do. But don't write it out just because it takes a lot of time to write all this out. And time is really of the essence on those multiple choice
But it's fun.
questions. So now we can start evaluating these. If C is going to 2 from the left, that means we're plugging in something ever so slightly smaller than 2. And so when we do that minus 2, we're pretty much 0, right? The ln of 0 is
1, 0, 0.
Error. It is an
the
error.
ln of 0 is an error. The graph of ln looks like this.
You betrayed me.
We can't take it, it's technically a negative infinity.
Yeah, I was supposed to say wouldn't it be negative?
Adding or subtracting other things to this are not going to fix it. So we can really just stop here. We could go on and keep evaluating, but we're not going to be able to fix the problem that we already have an infinite amount of area here by adding or subtracting other values to it.
Divergent.
So that means that this area is divergent.
What if we added infinity and then figured out which infinity was bigger? Or
Good
something?
question. So we do know that infinity minus infinity is not equal to 0 necessarily. So we are actually going to over here get another infinity, and we may be inclined to think they would cancel each other out, or to at least try to do a L'Hopital's on this. You cannot combine infinities from separate limits. Okay, so we really have 2 different parts to this problem because we separated our integral. We have this first part where we were considering the limit 2 from the left, and then we have this second part of the problem where we're considering the 2 from the right. Within those, if we would end up with like an infinity minus infinity, then we do need to consider a L'Hopital's rule, because that might actually end up being something. But if you would get an infinity like in the blue group and another infinity in the green group, we can't do a L'Hopital's rule across those 2 limits. So there'd be no way to cancel that out.
Okay, so it'd be in. What would the answer be if it was like negative infinity plus infinity? Would that just be the
Then
answer?
we would need to do a L'Hopital's rule to find out what that is,
Okay.
because negative
Oh,
infinity
yeah,
plus infinity is not something that
Yeah.
we can answer.
L'Hopital's to like dx over x minus 2?
No L'Hopital's rule to our limit, to this. We would have to combine those together and make a fraction out of like what's in the blue box and do a L'Hopital's rule on that limit, not on the original question, but on our limit.
That's annoying.
L'Hopital's rule is only done on limits.
That's a good thing we don't have to do that, because it'd be really rushed.
It actually wouldn't be terrible. What do you do to combine 2 logs together when they're subtracted?
Divide them.
Divide them. So this is going to end up being the ln of absolute value of c minus 2 over the absolute value of 1 minus 2. And I mean, it wouldn't be terrible. But still don't want to do it, and we don't have to do it. But
Isn't that, you say ln of the absolute value of that stuff?
yeah,
Isn't
yeah.
that still not a fraction then? Because isn't that all one piece?
The problem would come in the fraction part of that, not the ln part of that.
Yeah, what's the derivative of?
But we can't do that here because this isn't indeterminate. This is infinity, and then this would be the ln of 1, which is 0. So this is negative infinity minus 0. So it's not indeterminate. We can't do that here. But having like an infinity in the blue one and an infinity in the green one, those can't fix each other.
This is kind of going back, but when we did the thing with the arctangent
Mhm.
derivative, Is it when it's negative that it's cotangent is the derivative? Or when it's
Yeah, so on that example, we were integrating a 1 over 1 plus x squared. If it was a negative there, then that would be our cotangent, yeah.
But you can just factor out the negative out of the integral, or like take a negative 1 out of the integral and then make it tangent or something.
Good question. We should be able to factor out a constant. So just doing this as it is, I guess would give arc cotangent. If we factor out that negative, it would give a negative arc tangent of x. It must be that those end up being the same thing.
Okay. Wouldn't that be true for the other arc?
Yeah, for the other co-functions.
Yeah.
Yeah.
Alright.
Good question. I've never thought about that, but I guess they would have to be the same because those are both valid ways of solving the problem.
Is infinity minus infinity 0?
No. Infinity minus infinity is indeterminate.
It might be 0.
It might be, but it's not always 0.
Or to be 4, or to be infinity.
Sometimes when we do these integrals, we care about if they converge and what they actually converge to. So if it converges, what is the actual value we get? How much data is truly there? Sometimes we just care about whether or not they converge. So does it converge or does it diverge? So we have some tests that we can do that will tell us about whether or not it converges or diverges. If it converges, these tests will just tell us that it converges, not what it converges to. So we're going to begin this with an example. And it's example 6. It asks, does the integral from 1 to infinity of e to the negative x squared dx converge? All right. That's a really messy function to try to integrate. To be honest, I'm not really even sure where we would go with trying to integrate this.
Let's do it.
We can't do a u substitution, maybe some sort of a by parts, but it's definitely not something that we want to integrate if we don't have to. So if all we're concerned about is does it converge or does it diverge, not what it would actually converge to in the case that it does converge, then we have some things we can do to try to test convergence.
I'm sorry.
What we want to do, our first type of test we can do is find a function that is more simple than this one, that in the end behaves pretty much the same. So what we're going to do is compare this function to the function of just e to the negative x. Because that's a whole lot cleaner. And what we want to do is think of how do these two functions compare. So we could do that by graphing. And the e to the negative x squared function, it looks like, oh, that's too harsh of a turn, but it kind of takes a little turn and then drops off. Then the e to the x function, negative x function, goes like this, and it also drops off to an asymptote. So they're both heading towards an asymptote, and after some point, the e to the negative x function is always bigger than the function that we're concerned about. Okay. So if this e to the negative x function converges, so we're considering the integral from 1 out to infinity, and 1 is actually where these things intersect. So if this area is convergent and the purple area that we're concerned about is smaller than that, then that should be convergent too, right? So if that whole area that's blue turns out to be like 2, okay, then that means the purple area should be smaller than 2. There's no way that that purple area could be infinity if that blue area is 2. Right?
Yeah.
So what we're going to do is integrate the blue one and see what happens with that. Because that's a whole lot easier to integrate. So this we can integrate. We need to do a limit as b goes to infinity. When we integrate, we get negative e to the negative x. When I plug in, I get the limit e goes to infinity, negative e to the negative b minus a negative e to the negative 1. Negative e to the negative b is the same thing as like negative 1 over e to the b. Negative exponents can go to the bottom. So if b is becoming infinity, then e to the infinity is
Big.
e to the infinity is
Huge
infinity,
Oh.
and negative 1 over infinity is
Really
0. So I end up then just getting e to the negative 1. So that entire blue area is e to the negative 1, or 1 over e. The purple area is smaller than that. I don't know how much smaller, but it must actually be convergent. So by doing this comparison, we can find out that that purple area is convergent. We cannot find out what it is convergent to. We know it is less than e to the negative 1, but we don't know how much less than.
Never mind.
So if you see a
I
question
thought
like that,
process, but
if you see a question like this on a test, it'll like give you like some ugly looking function. I can't even think of what it is.
true or false? This is
Right, so
convergent.
this is a rough
Yeah.
question for multiple choice
Yeah.
because
There's two
they're not going to
choices.
say like convergent, divergent, blank, blank, blank,
Pi.
right?
Raised
No,
by
So this is a rough type of question for a multiple choice. It is more likely to see something like this on a free response.
Where would you go with this? Would you have to, what we learned?
On the free response, we'll learn some more tests, but on
Okay.
the free response, it would be, here's your function. Part A, is this integral convergent or divergent? Explain or justify your answer. Okay. So this would definitely be a more likely free response because, otherwise multiple choice, we only have
Yeah.
two options, converge or diverge.
I was trying to make it
So-
multiple choice and it really tricky.
Yeah, no, this would be a more likely free response.
Some partners you guys are. You sure there's no true or false on the calc test?
There is no true or false.
Awesome.
There's no matching.
Except
It's
if
so
you
good. Just multiple guesses.
No, you have to come up with your comparison
I
function.
know.
So highlight.
So, what we just did
I'm sorry. I just.
is called our direct comparison test. So the direct comparison test says that if we can find two functions, a function f that is always going to be at least smaller or equal to a function g after some point. Okay. They can cross each other and equal each other as long as after some point pretty far down the road, one of them starts to dominate on top of the other one for the rest of the time. Yeah. So then the integral of f, the smaller one, will converge if the integral of g converges, because g is bigger. So if that bigger area is a number, then the smaller area can't be infinity. It has to be a number also.
What if G diverges?
If g diverges, we know nothing.
Well, we know G diverges.
We know g diverges. We know nothing about f. F could still converge, it could also diverge. Okay? So if g converges, that's going to squeeze f down to having to converge as well. If g diverges, we know nothing about f.
However, if F diverges, then we know G diverges also.
Yes.
So if we have a problem like
You
that
can't be-
and
this is-
we see that G diverges, does that usually mean we picked the wrong function to compare it to?
Yeah.
So there
Yep.
should be something
So
else there.
when you're choosing your g function, well, Okay, yeah, when you're choosing your g function, you either want to choose a function that is larger than f, that you know is going to be convergent, or the other option, part B here, says not the right thing. This is not the right thing, is what it says. So in part B here, it needs to say if f diverges. Oh, no, I'm reading it backwards. Never mind, we're good. I don't know why I wrote if and only if statements backwards, but if f of x diverges, then g of x will diverge as well. And so what that says is if the smaller one is divergent, it's going to push that other one off as well. If the area under the purple curve is infinite, how could a bigger area not be infinite, right? So if the top one converges, it's going to squeeze the bottom one down. If the bottom one diverges, it's going to push the top one off. So when choosing your function, you either want to choose a function that is bigger, that is going to converge, or a function that is smaller, that's going to diverge. Because that will then give us information about the function we want to know about.
So in order to find out if it's bigger or smaller at like a really long time, should we just plug in big numbers for x and see which one?
Yeah, or you could graph them
Oh.
and kind of look and see which one's ending up on top. Or, yeah, that would be best. Because if you did like a limit as x goes to infinity, they're likely both going to be 0.
Well, yeah.
So that's not really going to help you. But yeah, graphing would be a good option.
On the e to the negative x and e to the x squared example, like if they're that similar, can you usually assume that they have the same, they both either diverge or converge?
Good question. There's another comparison test that we'll talk about that uses a little bit more of that logic. And again, when we do these tests, it only tells us that it converges or that it diverges, not what it actually converges to if it does converge. Okay, so we'll look at example 7 now. Example 7 gives us, it's actually a couple of examples separately, but first we'll look at the integral from 1 to infinity of sine squared of x over x squared dx. There's no way I want to integrate this. So if it doesn't ask you specifically what it converges to, just if it converges, then this is where comparison tests are really good. So what I want to do is find a function that is always going to be either bigger or smaller than this given function. So the really messy part of this is that sine squared of x. Right. What do we know about sine in terms of its values?
Between 1 and
1
0.
and negative
Okay, it's between 1 and negative 1 always, right? That's as big as it can get, 1 to negative 1. What about if I square it?
Same.
It could get higher than 1 or negative.
No,
The amplitude
It's
goes up.
between 0 and 1.
Between 0 and 1, right? Because if you square a negative, it becomes positive. So if I'm squaring it, the biggest it's ever going to get is 1. So that means that this must be smaller than or equal to 1 over x squared. There is no way that sine squared is ever going to be bigger than 1. It can't be.
That's a lot easier.
So then, if we integrate this, or if we think about an example that we did yesterday, does this converge or diverge? This converges. This was our P example. If the power in the denominator is 1, it is divergent. If that power is bigger than 1, it is convergent. Even 1.000001, okay? Any power bigger than 1 down there is going to be convergent. We don't necessarily care what it converges to, just if it converges.
Is it only when 1 is
Isn't
on
it
top?
that weird?
No, it's only if a constant is on top.
Okay.
Good question. So it could be any constant on top.
Even
If it was a 2 on top, the area would be twice as big, but we don't actually care what the area is.
Okay.
as long as it's a constant, not a variable.
Don't we know what it'll be converting to?
We can know what this will be converted to, but for the context of this problem, we don't really care.
What's it equal to again? Because I can't read what I had before. It'll be like.
Check your book. I don't have it memorized because it's not worth my time to memorize, which means it's not worth your time to memorize either.
Oh, but I was memorizing random junk.
This
Remember my LN rule?
function was bigger than our function, and this function converged. That means it's going to squeeze our function down to converge as well. Okay, so that means that this thing is convergent. We just have no idea what it converges to.
Hold on. No.
You say this every day.
Isn't just to refresh my memory, isn't a fraction divided by fraction something bigger than the original?
Math
The,
never didn't have concepts in it.
The constant on top.
We were learning. Yeah, I had addition,
Still the
subtraction,
concept. Yeah,
those
those are the
concepts.
concepts.
Is this a separate problem or is it?
A separate problem. Same type of problem. There's just like an A and a B example in here.
Last problem.
Yeah, concepts. Polishes, things.
I do not want to integrate this.
I have a quick question.
Yeah.
So if we have, say, something smaller than 1 on top of the last question we did, and then you divide it by something that's really, really small, isn't that a really big number?
Yeah.
Because it says that the sine of x squared is going to be smaller than 1 over x squared, so let's say
No,
sine x
it
squared
doesn't
is
say that. It doesn't say that the sine of x squared is going to be smaller than 1 over x squared. It says that the sine squared is going to be smaller than 1.
Okay.
I only changed the numerator.
Oh, okay. Never mind.
For this example, I don't want to integrate this. So what I want to do is find a function I can compare this thing to. When we're talking about infinity, subtracting 0.1 is not such a big deal. When we're talking about infinity, subtracting 1,000 is not such a big deal.
And in some
Right?
cases,
So really I can ignore this negative 0.1, and this thing becomes
X.
pretty close to just an x on the bottom. Okay, so the square root of x squared. Now the question is, which one of these is bigger? For really big numbers of x. So in the first
The
one,
right one.
I take a really big number, I square it as a really big number, I subtract a tiny bit from it, it's still a really big number, take the square root of it. Is that going to be bigger or smaller than what the number
It's going to be
was
slightly
Bigger.
smaller.
originally?
Bigger.
Slightly
Bigger.
smaller.
It's gotta be bigger.
This is going to be slightly smaller, the denominator. With a slightly smaller denominator, that means the fraction is going to be
Bigger.
slightly bigger.
A tenth smaller.
Okay? That denominator is going to be slightly smaller, which makes the fraction slightly bigger.
It's gonna be like
100. That's going to be 100 smaller.
So-
That would take me off if I was that infinity.
We are then going to think about
That was a concept.
the integral of our comparison function. And we could actually integrate this, or we could think about examples from yesterday, and what do we know about this guy?
This is equal to
That's
0.
divergent.
That is divergent. Okay? When the power in the denominator is 1, it is divergent. When the power in the denominator is greater than 1, it will be convergent. So this is divergent. This one was smaller than ours. So the function we're concerned about is higher than this function. If this function has infinite area and our function has more than infinite area, our function has infinite area and is thus divergent.
If you're adding something to something that has a power greater than like if you had x squared plus 100, would that still be convergent? Or if you had 1 over x plus 100, would that still
Yeah,
be
the
convergent?
the point one didn't really change. Oh, if it was adding, then this denominator would be bigger, which would make this fraction smaller, and reverse this, and this problem would be inconclusive.
Yeah, but I meant like on the 1 over x, if you
Yeah.
added like a number to it, would
Oh,
that change it?
it would still be divergent.
In the same
Yeah.
with 1 over x squared.
Yeah. We have another test we can do, which is called the limit comparison test. And this is more what David was thinking in terms of if the functions are acting pretty much alike, can't we just say if one of them converges, the other one will too? And that's what this limit comparison test is going to say. It's going to say if the limit as we do one of the functions over the other one is some constant value. This is like what we did back in section 2. So in section 2, we did a comparison between two functions and we wanted to say which one was growing faster. Okay? We could also then think about if these are heading down to an asymptote, which one is shrinking faster. If we end up doing the fraction of one over the other and we get a limit, we learned in section 2 that means they grow at the same rate. If we don't get 0, if we don't get infinity, we get some number. The two functions are growing at the same rate. Or in the context of this, shrinking at the same rate because they're heading to an asymptote. If they are shrinking at the same rate, they will do the same thing. They will both converge or they will both diverge. Okay? So again, we're going to pick a function to compare our function to, and we want to pick a function that's going to behave almost exactly the same. Okay? If they behave almost exactly the same, then they will both converge or they will both diverge. So example. We could actually integrate this and evaluate it to decide if it converges or diverges. If we integrate it, what do we get? Arctangent. So we could do it.
Yes.
We're going to have to evaluate arctangent stuff. If the directions say, if it does it diverge or if it converges, what does it converge to? Then we need to go ahead and integrate this thing. If we need to actually know what it converges to, if it converges, you have to do that by integration. Comparison doesn't tell you what it converges to. If the directions just say, does it converge or diverge, then we can do a comparison.
So on the last one with the square root of x squared minus 0.1, we said that the 0.1 was, like, you could ignore it because it's going to infinity. So could you just ignore the 1 on this one, and then it'd be 1 over x squared, which is conversion?
Yes. So we're going to choose a function to compare this to and say that in the long run, adding 1 is not such a big deal. So these should be approximately the same thing. We need to actually confirm that they really are growing, or in this case, shrinking at the same rate. And we do that by doing the limit as x goes to infinity of one of them over the other one. It doesn't matter which is which. How do I divide fractions?
Just switch them.
You mean just switch them?
So 1 plus x squared on top and x squared on the bottom.
How do I divide them?
You multiply it by the reciprocal.
Multiply by the
If you wanna
reciprocal
do
of the
that.
bottom one.
It's a lot faster. Just switch it.
That's not mathematically correct.
It is a lot faster.
Yeah.
It doesn't work.
I mean,
but-
it's, now if it was like 2 over x squared, then yes, you'd have to. It'd be
You switch them
You just
and get rid of the
switch.
ones if they're one.
So this is
Yeah,
really
exactly.
all one fraction, and I can
Kind
take
of.
that
like
denominator
You take the denominator of the denominator
and divide
put
it
on
into
top.
both parts.
Then you take
And
the
so I end up
denominator.
getting 1 over x squared plus 1.
It's so much easier.
If x goes to infinity, infinity squared is infinity, 1 over infinity is 0, and this thing is equal to 1. That means these two functions grow at the same rate, and we can apply this limit comparison test. You have to do this limit part to show that what we're doing is valid. The limit comparison test says that the limit of the given function and our chosen comparison function as x goes to infinity needs to be a number other than 0 or infinity. Doesn't matter what the number is, as long as it's not 0 or infinity. So you have to do this comparison of limits to show that we do get a constant. Once we do that, we can say they do the same thing. So then, we could say, if this were a free response, we could say like our function, if it was called f of x, converges because 1 over x squared converges. And we could say, in here it'd be even better to say by limit comparison test. And give what rule we're applying to this.
The constants added to a variable don't really matter as long as they're.
As we're heading limits to infinity, true.
Okay.
In general,
Um,
like the ones that make them.
for example 9,
Long notes.
for example 9, we could maybe integrate this. No, I haven't tried. But if the directions just say, does it converge or diverge, then we don't need to bother with integrating if we can find something to compare this to. As we go to infinity, subtracting 5 is not such a big deal. So we're going to say as we go to infinity, this thing is basically the same as 1 over e to the x.
Which is.
We need to show that they are basically the same. And the way we do that is by taking the limit of one of them over the other one.
Yeah, anyways.
Flip over that bottom one and multiply. I can divide the e to the x into each part. Now, as x goes to infinity, e to the infinity is infinity. 5 over infinity is 0, and 1 minus 0 is 1.
Is it always gonna be 1?
It will not always be 1. It will not always be 1, but as long as it's not 0 or infinity, we're good. So now, our question is, what does 1 over e to the x do? Because they're both going to do the same thing, and the last one we just kind of already knew what it did because it was a function we had worked with before. We have not worked with 1 over e to the x, so we need to actually now think about this. How do I rewrite it so that it's easier to integrate? E to the negative x.
Yeah, that.
So then we did actually do this one a couple of examples ago, I think. Right? We did an e to the negative x. Yeah, in example 6, we did an e to the negative x, and we found it was convergent. So then we can say that this converges by limit comparison test with e to the negative x.
So if we knew like a general idea of which formulas converge and diverge, we could just go in and just get it over with.
Yep.
There won't be any points for like actually taking the integral of that, you just have to know that that will convert.
Yeah. I doubt there would be a point for actually showing the integration. If you just know it, they'll give it to you, because there's some that we just aren't supposed to know.
It would be the same dude.
One more example of an application, or one more part of our notes of an application. We'll see if it's one or two examples. Example 10 says find the volume obtained by revolving the curve x e to the negative x from 0 to infinity
Does that say the volume of an infinite?
When would we do that?
around
Honestly, no, when would we?
the x-axis. So we end up with something that looks kind of like a vase, except it's infinitely fluted, right? It goes out forever, but it is approaching an asymptote, so it's becoming very, very, very narrow at its top.
Because it says it's infinity.
How do we find the volume of a revolution? Integral of area.
With circles.
And it's going to be circles.
Yeah.
Pi.
Pi
The
r
circle
squared
is
and
pi
x.
r squared, and our radius is going to be
X
The
would
function.
be negative
the
x.
function, because we go from here to here. And we want to integrate that from 1 to infinity.
Can I take a stab at it and say that it's a lot?
Oh, I don't know why I put a negative.
I would
Okay.
guess you're wrong.
I think you're wrong.
Zero. I don't think it's zero.
It's not zero.
It's a constant, it looks like. Maybe.
To integrate this, we need integration by parts. So we're going to review that, since it's been a little while since we've done integration by parts. When we choose parts,
Not
what would be a good choice for the u function?
X squared.
X squared. Why is that a good function?
Because it's the cleanest.
Because it's the cleanest that comes first in Liate. And what will happen when we take derivatives of it?
Get
It will
2x.
It'll eventually go to
It'll
zero.
eventually go away, so this is an excellent candidate for tabular.
I was just looking at the e to the x to the e to the.
When we integrate the other, when you integrate, you get the same thing, divide by the coefficient for the chain rule. When we do it again, divide by the coefficient for the chain rule, and then do it again, divide by the coefficient for the chain rule.
Plus, minus,
Plus, minus, plus on our diagonals.
plus.
Now we really have pi times the limit as b goes to infinity of negative x squared over 2 e to the negative 2x minus 2x over 4 e to the negative 2x minus this minus there though.
Oh, yeah.
2 over 8 e to the negative 2x. And I don't need a plus c, because I need to go from 1 to b. Every single one of these terms has that e to the 2x in it.
At the end of negative.
So I could think about pulling that out as a negative 2x if I can put it down to the bottom. And then I'm going to have a negative x squared over 2, a negative x over 2, and a negative 1/4.
Shouldn't it be a 1 over e to the negative 2x in the beginning?
I put it in the beginning of everything. It's in every term, so I put it in the beginning of everything.
Yeah, there shouldn't be a negative 2x.
It went onto the bottom of the fraction.
Okay.
Negative x wants to go to the bottom. So now if I think about plugging in infinity, 2 times infinity is infinity, and e to the infinity is infinity, and 1 over infinity is 0. So plugging that whole b part in doesn't matter, so then I just have to do minus plugging in the 1. So I get that pi out front, I don't want to forget about that. Then I plug in the 1, and I get 1 over e squared, and plug in a 1, I get negative a half, minus a half, minus a fourth. And we could work out that arithmetic there. But that is the volume.
Why don't you plug in the infinity the other ones? Because one ends up being infinity times 0 then?
What a
I think
complicated
it would, but I don't think that's an indeterminate function.
Infinity times 0 is not indeterminate.
Yeah.
It is 0?
It's 0.
Oh, okay.
Yeah.
So why don't we call it B?
Because you can't actually plug in infinity, and these limits of integration have to be things that we can actually plug in. So I can plug in b, and then I can just let b get really big. But I can't actually plug in infinity.
You can put 2 times b, but you can't put 2 times
We're thinking about what happens if we plug in huge numbers. Yeah. It's a notational thing. Multiple choice doesn't matter, but otherwise we need it there.
Just call it a day, right there.
we are going to call it a day. That is the end of our 8.3 notes, which means your homework is the 8.3 homework.
Are you gonna be here after school?
I will. Today is the one day
Hey,
I will actually be here after school.
I have a test for you, Wait, how much time do we have left class?
We go to chapel. I don't know when.
Oh, the chapel's after this?
Chapel is after this.
Oh.
Because I only have one question I could not
That's why I
get. We have 5 minutes, I'm gonna ask you.
Chapel is, let's see,
We should have chapel.
we
They break our minds down and then build it back up.
end at 10 after. It's time to go to chapel.
Alright, never mind then.
What is your guys'
Get out of it.
thing you're debating?
Thank you.
I got my text corrections.
Yeah, did you get that? You
Thank
got my
you.
text message about me adding the stuff, right?
Yep. I don't know what you added, I didn't go check, because I was like, at church.
Let's hope the college campus has computers and the internet, so we can print that out.
I have a computer.
Oh, you brought yours?
I've always
I packed my computer up, but I was in such a hurry to get to 0 hour keeper that I forgot.
Nice.
When you asked about an extra gesture, I just laughed. I don't have an extra white one, but I have like 14 or 15 extra gestures.
Yeah,
See,
I thought
I
my dad
brought-
grabbed it.
I brought all that stuff, I just didn't wear it.
Yeah,
I'm gonna wear it tomorrow or tonight.
Mine's in my car.
Mine's in my car too.
I have one jacket, one shirt, one bag.
I thought we agreed. I know we agreed to wear black suit, black tie,
Yeah,
but I
just
thought
not to school.
well, you should have specified that part.
I did yesterday in 4th hour.
Of course, I have gotten several compliments from several fairly attractive people, so I'm okay with this.
Alright,
Including your girlfriend?
Yes.
good.
No, she was not on that list. I didn't get a compliment for her, but she doesn't qualify on that list.
That's what I thought you said, and I'm like, Travis, no problem.